All right, so now we're ready to begin our very first unit of the year, which is kinematics. This is going to be the study of how things move. That's how we're starting out here. Just two quick notes, since this is our first real content video. Number one, please do make sure that you take notes while you're doing this. Ask questions, okay? That's going to be important. We will always have time in class to go over them. So just jot them down as you're going through because you probably, as I've said before, definitely not the only person wondering those things. The second thing is pay attention to the things in blue. These are going to be really important concepts that you need to really know and you need to just have down cold as we progress throughout the year and for the AP exam. So keep those in mind. Those are why they're written in blue. So we've already talked briefly in class, or we will talk in class, about what really makes an amusement park ride exciting. And the key to that is not going fast, as many people think, but changes in your speed, changes in motion, which we in physics call acceleration. So the technical definition here is the rate of change of the velocity, okay? For those of you that are in calculus, you'll eventually start talking about how this is a derivative, but really the rate of change is a measure of how quickly, okay, that's what that rate of change means, how quickly the velocity changes, okay? Notice this is in blue, by the way, meaning that this is an important concept. This is something that you have to know throughout the year. I personally like a slightly different form of the definition, and that is that acceleration is how quickly an object does one of three things: either speeds up, slows down, or changes direction. Okay, so those are the three ways that we can accelerate. We can either speed up and go faster, we can slow down and go slower, or we can turn and change directions. And acceleration measures how quickly, all right, there's that rate of change piece again, how quickly that transition happens. Okay, so it's all about the change. That's really the key idea with acceleration. Acceleration is changes in motion. Since we are talking about how acceleration is the rate of change of velocity, we probably should take a second to define velocity. I think most of you probably have a pretty good idea of what velocity is, but once again, we have our technical definition, the rate of change of the position, okay? Once again, velocity is a rate of change, so it's how quickly your location is changing. That's another way of saying your velocity, how fast you're moving, how quickly your location is changing. So if your velocity is 5 meters per second, it means that every second your position is changing by 5 meters. Okay, or 30 miles an hour. Every hour your position is changing by 30 miles. So velocity is the rate of change of the position. Okay, the slightly less technical version of this is that velocity is how fast an object is moving and in what direction that object is moving. Velocity is similar to speed. That's kind of the word that we typically use more often in everyday language. There is a technical difference between velocity and speed, which we'll get into in a little bit. Anytime we're talking about velocity, we're always going to have units for it of distance over time. So miles per hour would be an example of a unit for velocity. Our standard is going to be meters per second. One thing that I cannot emphasize enough here is that velocity and acceleration are not the same thing. Velocity is how fast you're going. Acceleration is how quickly your velocity is changing. That's really the key difference. So they're related, but velocity and acceleration are not the same thing. We'll work more with this, but it's completely possible to have a very, very big velocity and a small acceleration and vice versa. There's nothing that says that can't happen. Okay, before we go on and kind of bring this all together, we need to talk about 3 quick tangents, all related to just some technical things with numbers that we're going to use throughout the year. The first is the difference between vectors and scalars. So the key distinction is that a vector is a number that needs a direction. It's usually represented by an arrow because of that, because it has a direction along with it. A scalar, on the other hand, is a number that does not need a direction. So the quick test for this that I always tell people is if you can put a direction after a number and it still makes sense, it's a vector. If you can't, it's a scalar. For example, if you said that an object had a velocity of 18 meters per second west, that makes sense because velocity is a vector. If you said that you push something with 200 pounds of force north, that would make sense because force is is a vector. If you said that an object has a mass of 18 kilograms west, that does not make sense. Mass is a scalar. It's a number that does not have a direction associated with it. So the key distinction here is that directional piece. Vectors are numbers that come with a direction. One term that you'll hear when we're talking about vectors is this term here, magnitude. What magnitude simply means is the size of whatever the quantity is, simply the number. So if we're talking about a vector has a magnitude, a size to it, and a direction. So we have an example here that if an object has a velocity of 30 miles per hour north, the magnitude is 30 miles per hour and the direction is north. So magnitude is simply the number itself, and then if we're talking about a vector, it has a direction in addition to that. If we're talking about a scalar, there's only the magnitude, like an object having a mass of 20 kilograms. 20 is simply the magnitude, and there is no direction. Our second tangent here is going to be about how we represent vectors. So there's really two ways that you'll see that we represent vectors, either symbolically in drawings where we use an arrow to represent the vector, or numerically. When we're doing a vector symbolically with an arrow, the length of the arrow is going to give us an idea of the relative size or magnitude, that word we were just talking about, of the vector. So we see at this example down at the bottom, this arrow is bigger than this arrow. That means that this quantity, whatever it is bigger than this quantity. So we can get a relative size of which vector, whether it's velocity or force or whatever we're talking about, is bigger, has a greater magnitude. In terms of numbers, the magnitude is simply represented by the number itself, obviously, specifically the absolute value. So this vector has a magnitude of 15, whereas this one has a magnitude of 5. So that's how we represent the magnitude if we're just talking about numbers. The direction is going to be either the direction of the arrow, which is pretty obvious, right? This vector clearly is going to the right. This one is to the left if we're talking about representing vectors symbolically. If we're talking about representing vectors with numbers, the sign is going to represent the direction. So in physics, sign, when we're talking about a vector, that sign simply indicates the direction, and that leads us nicely into the next tangent, and our last tangent. In math class, your math teacher probably told you that -8 is less than 6. And in the math world, that's correct. But in the physics world, when we're talking about a vector, that is not correct, and here is why. If we have a velocity of -8 meters per second versus a velocity of 6 meters per second, the -8 is actually the greater velocity. That object is moving faster than the 6 meters per second. The difference and the meaning of this negative sign is the direction. The object with a velocity of -8 meters per second is moving in the opposite direction from the one that's going at 6 meters per second. So one might be going that way, whereas the other is going that way. And that's all that negative sign means. So you might be thinking to yourself, which direction is negative? We do have a standard convention, and it matches up with a typical graph. Up and to the right are traditionally the positive directions, down and to the left are traditionally the negative directions. What I will tell you is the most important thing is being consistent. If you don't want to do that, if you want to make up negative and right negative, that's perfectly okay, but you have to be consistent. That's the biggest thing, is you have to be consistent with your sign conventions. And this is something that I will harp on throughout the year. There are many people that lose points on quizzes, tests, etc. because of signs. So it's something that we're going to be working on from now until even after the AP exam. So now that we've been on our two tangents, let's go back to the idea of velocity and acceleration and use what we just learned about vectors and signs and directions and apply it to velocity and acceleration. So let's go back to the three ways which we can accelerate, which, as a refresher, are speeding up, slowing down, and changing directions. And we have three examples here of three different cars. One speeding up, one slowing down, one is changing directions. So which one is which? This might be fairly obvious, maybe not, but the The first one here, where the acceleration and velocity are both in the same direction, that is an example of an object that is speeding up when both of them are in the same direction. This car here, where they're in opposite directions, the car is continuing to the right, but obviously because of the cliff is slowing down and accelerating to the left. That is an example of an object that is slowing down. And lastly, we have this case where the velocity is in one direction, the acceleration is not in the exact same direction, nor is it in the opposite direction. And this one is an example of changing directions. If we want to get technical, there is a little bit of speeding up here as well, because we see that some of the velocity and acceleration kind of match up. It's not completely perpendicular. So the acceleration's a little bit in the direction of the velocity, but not exactly in the same direction like it was in that first example. So what conclusions can we draw from this? And this is another important concept. Objects are speeding up when the velocity and acceleration are in the same direction. Objects are slowing down when the velocity and acceleration are in opposite directions. That's the key determining factor. So if you're ever trying to figure out whether or not an object is speeding up or slowing down, all you need to do is determine the sign or the direction of the velocity and acceleration. Remember, because the sign indicates that direction. So if they're the same, we're speeding up. If they're opposite, we're slowing down. Bringing this back to that idea of signs, as I was just talking about, we can determine whether or not we're speeding up or slowing down simply based off of the sign, because that sign indicates direction. So if both our velocity and acceleration are positive, we are going to be speeding up. If our velocity is positive and acceleration is negative, that's slowing down. If our velocity is negative and our acceleration is positive, that's slowing down again. And if they're both negative, they're back to being in the same direction, so they're speeding up.